Chapter number 4, Trigonometric Ratios. Now consider this triangle PQR and let's get a recap of what we already know. In this figure, PQ is the hypotenuse, PR is the opposite side to angle X, QR is the adjacent side to angle X. We know that sin X is equal to PR over PQ, cos X is QR over PQ, and tan X is PR over QR. We also know that tan X is equal to sin X over cos X. We now want to derive a more complex relationship of these trigonometric functions. Considering this smaller triangle ABC, sin X is equal to AC over R, and therefore AC is equal to R sin X. That's simple cross multiplication. We call that equation 1. Equally, cos X is equal to BC over R, and therefore BC is equal to R cos X, and we call that equation 2. Using Pythagoras theorem, AB squared is equal to AC squared plus BC squared. Substituting the values of AB, AC, and BC, we get R squared is equal to R sin X squared plus R cos X squared. That gives us R squared is equal to, opening those brackets, R squared times sin X squared plus R squared cos X squared. Sin X squared is the same as sin squared X, and therefore we shall have R squared is equal to R squared sin squared X plus R squared cos squared X. If we divide both sides by R squared, we shall get 1 is equal to sin squared X plus cos squared X, and we call that equation 3. It is also true that tan squared X is equal to sin squared X over cos squared X, and we call that equation 4. Now rearranging equation 3, we can have sin squared X is equal to 1 minus cos squared X. If we substitute that into equation 4, we shall have tan squared X is equal to 1 minus cos squared X over cos squared X. If we split that into distinct fractions, we shall have 1 over cos squared X minus cos squared X over cos squared X. That fraction will cancel out the cos squared X and we shall remain with 1. And so we shall have tan squared X is equal to 1 over cos squared X minus 1. If we bring 1 to the left hand side, we shall have tan squared X plus 1 is equal to 1 over cos squared X. Now, consider this right angle triangle ABN with the hypotenuse of 2 units and one of the shorter sides is 1 unit. We also have one of the acute angles, 60 degrees. We want to use this triangle to prove that these relationships are indeed true. But first we find the missing side. Using the Pythagoras theorem, we shall have bn squared plus an squared is equal to 2 squared. 1 squared plus an squared is equal to 4. An squared is 3 and an is the root of 3. Sin 60 is equal to an over 2 and that is equal to root 3 over 2. Cos 60 is equal to 1 over 2. Sin squared 60 plus cos squared 60 will therefore be equal to root 3 over 2 squared plus 1 over 2 squared. That gives us 3 over 4 plus 1 over 4, which is equal to 4 over 4, and that is equal to 1. And therefore sin squared X plus cos squared X is indeed equal to 1. We take a few examples. 1. Given that sine alpha is equal to 1 over 2 and sine beta is equal to root 3 over 2, where alpha and beta are acute angles, find sine alpha cos beta plus cos alpha sine beta. Now, given that alpha and beta are acute angles and that sine alpha is equal to 1 over 2, it means that we had a right angled triangle and that the hypotenuse was 2. If we mark this as alpha, then it means the opposite side here is 1 unit. We can find the missing length using the Pythagoras theorem. If we call it b, then we shall have b squared is equal to 2 squared minus 1 squared. That is 4 minus 1, and b is equal to root 3. And that is indeed why we were given that sine beta is root 3 over 2, and therefore beta is here. With this now, we can find all the trigonometric ratios. Cos alpha will therefore be equal to root 3 over 2 adjacent over hypotenuse, and cos beta will be equal to 1 over 2. Therefore, we shall have 1 over 2 times 1 over 2 plus root 3 over 2 times root 3 over 2. That gives us 1 over 4 plus 3 over 4, and that is equal to 1. Example 2. Show that sine squared x plus cos x over cos squared x is equal to tan squared x plus 1 over cos x. Now we want to prove that the left hand side is equal to the right hand side. So we take the left hand side, split that into separate fractions. Sine squared x over cos squared x plus cos x over cos squared x. Recall that sine squared x over cos squared x is equal to tan squared x plus cos x goes once. Cos x into cos squared x will divide into cos x times. So we shall have tan squared x plus 1 over cos x. And we have proven that to be true. Third example, show that cos squared x over sine squared x plus cos squared x is equal to 1 over sine squared x minus sine squared x. Again, we prove that the left hand side is similar to the right hand side. We simply do our manipulations. First thing, cos squared x over sine squared x plus, make the next one a fraction, that is cos squared x over 1. Find the LCM of sine squared x and 1, that is sine squared x. Sine squared x divides into sine squared x once. 1 times cos squared x is cos squared x, plus sine squared x divides into 1 sine squared x times. Multiply that by cos squared x, and we shall have sine squared x times cos squared x. But then we know that sine squared x is equal to 1 minus cos squared x. So we substitute sine squared x with 1 minus cos squared x. And we shall have 1 minus sine squared x plus sine squared x times 1 minus sine squared x, everything over sine squared x. Open that bracket, we shall have 1 minus sine squared x plus sine squared x minus sine to power 4 x, everything over sine squared x. Minus sine squared x plus sine squared x is 0. And so we shall remain with 1 minus sine to power 4x over sine squared x. We break that into distinct fractions, and we shall have 1 over sine squared x minus sine to power 4x over sine squared x. Sine squared x will divide into sine squared x once and into sine to power 4x sine squared x times, and so we shall remain with 1 over sine squared x minus sine squared x. Next, trigonometric graphs. Now, when we plot trigonometric ratios against their corresponding angles, we obtain trigonometric graphs. For example, when angles are plotted on the x-axis and the sines of those angles on the y-axis, we obtain this graph. It is called a sine wave. We say it's periodic because it repeats itself after some distance or periodically. This is a graph of the function y is equal to sine x, where x is the angle, which could be in degrees or radians. Just remember pi radians is equal to 180 degrees. The maximum or minimum value of the graph is called the amplitude. In this case, the amplitude is 1. The graph repeats itself after 360 degrees or 2 pi radians. So the graph has a period of 360 degrees or 2 pi radians. The distance between two successive crests or troughs is called the wavelength. In this part, we shall look at some transformations that can happen on the graph when we change the base function. We shall use the sine wave, and so the base function is y is equal to sine x, and the brown graph is our base graph. So we shall see what happens when we manipulate the base function. The first transformation is the A transformation. There is a constant multiplied to the function, so we call it a graph of y is equal to A sine x. When a constant is multiplied upfront to the function, it produces a sort of vertical stretch or compression to the graph. This is the base graph y is equal to sine x. And now let's make an A transformation. Let's have y is equal to 2 sine x. And you see our graph has been vertically stretched by a factor of 2. Where we had crest at 1 and -1, now we have a crest +2 and a trough of -2. So each function value has now been multiplied by 2, and the result is stretching by a factor of 2. If we look at 3 sine x, everything has been vertically stretched by a factor of 3. The positives have become more positive, and the negatives have become more negative. So multiplying by a factor that is more than 1 produces this stretch. And if we multiply by a factor between 0 and 1, we will see a vertical compression. We multiplied by 0.4, so every function value is now 0.4 times what it was originally, and the result is a compressed graph. If we multiply by a negative number, the result will be like a reflection on the x-axis. So y is equal to negative sine x. The graph is exactly the same size as the base function, but it has been kind of inverted or reflected on the x-axis. So multiplying by a negative constant produces a reflection on the x-axis. If we multiply by a negative number but greater than 1, we will see both changes. We will see a reflection about the x-axis, and we will also see a stretch or compression. In this case, multiplying by -2.5, we have a reflection and a vertical stretch by a factor of 2.5. And so in general, when we talk of the A transformation, that A is the amplitude of the graph. On the base function, the amplitude is 1, and that is for 1 sine x. For 3 sine x, the amplitude is 3. Hope you can see that. Notice that when multiplying by a negative function, the amplitude will be given as an absolute value. It has no sign. And so for the function y is equal to negative 2.5 sine x, the amplitude is 2.5 and not negative 2.5. Now, the next transformation is called a D transformation, like y is equal to sine x plus d, where a constant d is added or subtracted at the end of the function. Let's see the effects of the D transformation. This is our base function, y is equal to sine x. The graph of y is equal to sine x plus 1 will see the entire graph shifted upwards by 1 unit. Any point we pick on the brown graph, if you move up by 1 unit, you will get to the green graph. Whether it's on the middle line or down the trough, up by 1 unit takes us here, or a crest, 1 unit up leads us there. Every point on the brown graph when increased by 1 unit will create the green graph. This is a result of the D transformation, adding some constant on the function. This one is shifted 3 units. If we subtract, we will accomplish a downward shift. This graph has been shifted down 2 units. The next transformation is called the B transformation, when we multiply directly to our variable x inside the function. Remember, A transformation accomplishes a vertical stretch or compression. The B transformation on its part accomplishes a horizontal stretch or compression. But there's a bit of difference. In A transformation, a number larger than 1 will stretch the graph, while a decimal number between 0 and 1 will compress it. In B transformation, it is exactly the opposite. A number larger than 1 compresses the graph, and a decimal number will stretch it. Let's see. This is our base function, y is equal to sine x. If we had y is equal to sine 2x, this is the graph. And so we see a sort of horizontal compression. If we can go back a little and look at 1.1x, and then increase the factor to 1.2, 1.3, 1.4, and you can see as the number increases, the graph is being compressed closer and closer to the origin. There we are at sine 2x. Sine of 3x gives further compression. And if you think about how the points move, we will see that each point on the brown graph, if you divide by 3, will get you to the green graph. That is, divide the x value by 3. This point here is at 90 degrees, sine 90 is 1. And where I get the y value of 1 is not at 90, but it's at a third of that. Divide by this factor 3. 90 divided by 3 takes us here, which is at 30. This point on the brown graph is at 180 degrees. We divide that by 3 and we get to our value of 0 at 60 degrees. One more point. Down here, negative 1 occurs at 270 degrees. 270 divided by 3 means we will see our first negative 1 value at 90 degrees. 270 divided by 3 is 90. And there we see that the function value of negative 1 is at 90 degrees. We know that this sine wave is periodic, and we are interested in this period, which is the distance it takes to complete one cycle. Both sine and cosine have a period of 360 degrees. If we look at sine 2x, which we know to be horizontally compressed, it is going to change the period. We are going to accomplish one cycle not in 360 degrees, but again divide this by factor 2. Now the period is 180 degrees or pi radians. And so in general, a B transformation affects the period of the graph. And given the period of y is equal to sine x is 360 degrees, the period of y is equal to sine bx will be 360 over b, or 2 pi over b. So for y is equal to sine 4x, let's see if we can confirm this pattern. One period of sine x is 360 degrees. 360 divided by 4 equals 90. And so we see one complete period in just 90 degrees. So in between these points, there are 15, 30, 45, 60, 75, and 90 degrees. So the rule is confirmed. If you take our initial period for sine and cosine, it's 360 degrees, and we divide by this factor, the coefficient of x. So when the number b is larger than 1, the graph is compressed. And when we have a decimal number, we see this horizontal stretch. In this case, we divide by 0.5 or simply multiply by 2. And so we are stretching that out. Our peak here, which was at 90, now is occurring at 180 after we divide by 0.5. This intercept is at 180 degrees. It's now intercepting at 360 degrees. And again, that's because we take these values and divide by the coefficient of x. Multiplying by a negative value like -1 will accomplish a reflection, but this time on the y-axis and not the x-axis. It looks like a reflection on the x-axis, but for purposes of consistency, like we will see, it's on the y-axis. The last transformation is the C transformation, where we have a constant C added to the variables, but still inside the function. This transformation produces a horizontal shift, either to the left or to the right. If you remember in the D transformation, it was a vertical shift. Positive D shifted the graph upwards, and negative D shifted it downwards. In this C transformation, the shift is opposite. A positive C shifts the graph to the left, and a negative C shifts the graph to the right. It is the opposite of what many people would expect. The base function is in maroon, and in green we have a C transformation. We added 90 degrees. It's added or positive, and so we are looking for a shift to the left. And we see the green graph is shifted to the left of the maroon graph, and by how many units? 90 degrees. So we can see a shift of 30, 60, 90 degrees. Every point on the maroon graph, if I shift left by 90, will land on the green graph. 30, 60, 90 to the left. If we look at these shifts in small bits, this is 18, 20, 30, and as we increase our value C, we can see the graph is moving farther and farther to the left. So the constant added will shift to the left, a constant subtracted will shift the graph to the right. But as always with these trig functions, there will be a few transformations that will lead to similar results. Consider shifting the graph by 2 pi radians or 360 degrees. Because 360 degrees is our period, if we shift an entire period, we will land at the same exact graph. If we shift by 180 degrees, here's a result we've seen several times before: a reflection on the x-axis and a reflection on the y-axis. And now it is appearing also as a result of a horizontal shift of 180 degrees. So we shifted to the left by 180 degrees, and it can also be seen identical to a right shift of 180 degrees. And so notice that different transformations can lead to the same results. Now, we need to cover a very important detail about the horizontal shift. We have sin x and sin x plus 60 degrees, and so we are shifting to the left by 60 degrees. If you focus here, we go back by 15, 30, 45, 60 degrees. If I look at this intercept, we go back 15, 30, 45, 60 degrees. And so we have a shift of 60 degrees. What if we decrease the periods of the function by having, say, y is equal to sin 2x and sin 2x plus 60 degrees? So we have both the b and c transformations. The period is decreased by 360 over 2, the coefficient of x. But how about the shift? We see a shift of only 15, 30 degrees. On the intercept, it is still 15, 30 degrees. And so clearly, changing the period is having an effect on the shift. In simple, to get the shift, we also divide the c value by b. That is 60 over 2 gives us 30 degrees, and that is our shift. If we had sin 4x and sin 4x plus 60, the period will be 360 over 4, that is 90, and the shift will be 60 over 4, that is 15 degrees. And you can see that from the graph. And so in general, for y is equal to sin bx plus c, the period is 360 over b, or 2 pi radians over b, and the shift is c over b. And remember, c could be a positive or negative. So in totality, if we had a function y is equal to a sine of bx plus c plus d, like minus 2 sine of 3x minus 180 degrees plus 1, the amplitude is a and is equal to 2. The period is 360 over b, that is 360 over 3, equal to 120. Phase shift is c over b, that is minus 180 over 3, gives us minus 60, and that means 60 to the right. The d value of 1 only means that the graph will shift upwards by 1 unit, but this will not change the other properties, that is the amplitude, period, and the horizontal shift. Tangent graphs are not very common because really they don't tell us much, or at least not at this level. Suppose we have y is equal to tan 2x plus 90 degrees. The amplitude is not used in tangent functions because there is no turning point. Phase shift is also not very common in tangents, but period is what we want to make a point at. For period in the trig functions, we look at the coefficient of b. We get our initial period or the base function y is equal to tan x and divide by b. It is important to know what is the period of a tangent function. It's not 360 degrees, it's 180. And so in this example, the new period will be 180 over 2, that is 90 degrees. And so this is the graph of y is equal to tan x. And so for y is equal to tan 2x, every point will be brought half as far from the y-axis as it was initially. And so this 180 degrees will be at 90 degrees, and the same goes for all other points. So this is tan 2x. Then we had a horizontal shift, so we divide c by b to get the shift. That is 90 over 2 gives us 45, and because it is positive, it is a shift to the left. There is our final graph for the function y is equal to the tan of 2x plus 90 degrees. Finally, graphical solutions of trigonometric functions. Now, we can use graphs to solve trigonometric equations. For example, on the same axis, plot the graphs of y is equal to sine x and y is equal to sine 3x for the value of x between negative 180 and 360 degrees, and use it to solve sine x is equal to sine 3x. First, we make tables of values for the two functions. This is the graph of y is equal to sine x, and this is the graph of y is equal to sine 3x. The solution for this equation, sine x is equal to sine 3x, is the x value for all points where the two graphs intercept. If we look at the graph, those values are negative 180, negative 135, negative 45, 0, 45, 135, 180, 225, 315, and 360 degrees.
The way we teach it in university and in high school as well, in colleges, is if you fall behind, you're in desperate trouble. That if you miss a class or miss an idea or don't do your homework, you go to the next class and the teacher assumes you know it, but it's like Greek to you. And so the biggest challenge is not falling behind, and the strategy is do whatever needs to be done so you don't fall behind. Seek help wherever you can find it, from students, from student help centers, from the teacher, from the teaching assistant, wherever you can get it. Because if you fall behind, it's like you're missing a floor in the building, you're missing a brick in the wall, and you just can't build the second floor without a good understanding of the first floor.